Hey fellow scholars, this is TechWithSherri. This reading session presents unified model that perform image, text and multimodal tasks using a pure pixel-based model. Many of the recent multimodal models are made of separate components for text and image, some of which have modality-specific training procedures. For example, the text component may require pre-training on mask-filling tasks. This paper explores an additional unification that uses a pure pixel-based model to perform image, text, and multimodal task. The proposed model was able to use a single encoder that processed both regular images and text rendered as image. As a result, the model does not require the typical tokenizing step for the text. This model performs image-based tasks such as retrieval and classification with almost the same performance as the state-of-the-art multimodal models. Further, the model achieved surprisingly good accuracy on visual question answering by rendering question and image together. So how does it work? Given an image and text sequence, first render the text into image using Google Noto font family. Then the two images go through the same convolution layer kernel before feeding into Vision Transformer model. The model is trained jointly using image-text contrastive learning. In other words, the image data and text-rendered images goes through the network and arrives at two separate latent representation. The contrastive loss is applied on the two latent representations such that matching pair of image and text are close in the embedding space and unmatched pair are more distant. This makes sure the encoder will output similar latent representation for pairs of image and text that describe each other. Of course, this would require constructing positive pairs and negative pairs. The positive pairs come with the training data, and the negative pairs is constructed by taking an image and pair it with another image's caption that does not match the given image. We have mentioned that the convoluted image representation goes through a vision transformer. So what is a vision transformer? In simple terms, vision transformer is taking the transformer encoder commonly used in natural language processing and applying it to a sequence of 16 by 16 image patches. Given a set of image patches, for every image patch, the model calculates how much every other image patch contribute to the prediction task on current image patch. This is called attention score. The attention mechanism does not care about the order of image patches. Therefore, the order has to be encoded into the input using positional encoding. For example, the first patch associated with number 1 has a learnable vector that has the same dimension as the image patch input. This positional encoding is concatenated with the linear projection of flattened image before going into the transformer. This is called the embedded patches. After obtaining the embedded patches and their corresponding attention, we can use attention score to compute list of embedded patch averages weighted by the attention score and feed it into the feed-forward neural network in order to generate a final latent representation of the image. With this setup of input, vision transformer, and contrastive learning, we can obtain a single vision transformer that provides a single representation that can be used to solve image text, and pure text tasks. This is a great progress on multimodal architectures. This concludes the reading session for this video. Does this get your mind going? Let me know in the comments below.